to like vertical asymptotes, horizontal asymptotes,
yeah, it's all about graphing rational functions, okay? And what is a rational function? It's a function that can be written as a fraction. So it's going to be a function that can be written as one function over another function. Okay, and a and b, these are polynomials, where a of x and b of x are polynomials. All right, so here's the first question. Okay, what's a polynomial? How would I? Yeah, there's, well, no, monomial is one term, but a polynomial, yep, is a set of monomials added together, right? So we have, the basic way to write it is a whole bunch of coefficients with descending order of powers of x, right? That mean, and n's have to be integers. N is a positive integer. Right? So that was a question on yesterday's test. Tell me which ones of these are polynomials. So a rational function, then, is a ratio of several polynomials. So, for example, we could have 2x plus 3 over x squared plus 5x plus 6. That would be a rational function. Okay, that's probably one of the more complicated ones that we would deal with. And what this section asks us to do is to visualize these functions graphically and to understand how the graph comes about. So unfortunately, we're back in the no graphing calculator because the concept here is understanding how these graphs come about. Okay, so we're going to get through the end of chapter 2 with a little calculator. You can use a calculator to reinforce what you're doing, to learn, but you want to understand how to make these graphs without the calculator. So if we were to say like f of x is equal to 3 over 1, right, that's just y equals 3. Technically, that's a rational function, technically. Okay, but it's not how we deal with rational functions. What we're really looking at is the fraction ones. How do we handle the functions that are fractions? We already know how to handle this one. We know this is a horizontal line. So we're looking at the fractions. Okay, the rational expressions are a function that's written as a fraction. All right, so if we take a look at the simplest one, was this. This was one of the 12 basic functions. Now remember, I'm going to give you a cumulative term 1 test. The 12 basic functions will be on that. What does that graph look like? What is that function? Yeah, like does this. It has these asymptotes. So I'm going to put a 1, 1. Everybody ground yourself on what this graph looks like. These are my 1, 2, my lines, right? Goes through 1, 1. It goes through minus 1, minus 1. And it does like this. It goes through those points. Okay, my stylus is not too great. That's the 1 over x. That's the reciprocal function. That's the most basic one. Now, what happens to that function if, instead of it being 1 over x, what if it was 1 over x plus 2? What would happen to that red function? It would move up 2. So rather than having this as our asymptote would now be up here. Oops, sorry. And we would have our function would look like this. This point would go up 2. This point would go up 2, and we'd have our function like that, right? So don't forget what we already know. So sometimes we can look at rational functions as transformations of that very basic one. Okay? What would that be? Move to the left 3. So rather than the point going through 1, 1, I'd go to the left 3, and my asymptote, rather than being at x equals 0, would be x equals minus 3, right? And here my graph would just have moved to the left 3. Okay, so we know how to transform functions, right? And now what we want to do is we're going to look at more complicated ones than these. Okay, let's look at one that's a slightly different. And let's analyze how do you figure out what this graph would look like without just typing that into your calculator. So why don't you go ahead, type it in your calculator. Remember, when you're typing this into your calculator, remember that you definitely want to put parentheses over the whole top and over the whole bottom. Okay, type that in. Right? In order to visualize these graphs, in order to graph them, there's 4 steps that we need to go through. We need to figure out what x values are not in the domain. And at those x values, is there an asymptote or just a hole? Where are the zeros? Where are the x-intercepts? Where are the y-intercepts? And where is the horizontal asymptote? And if we can figure out the answer to those things, we can graph this without a graphing calculator. We can picture this graph and we can think about different parts of it that we need to use.
So in the denominator, you find the zeros, and those zeros are what make the function undefined, so make the denominator equal 0.
Make the denominator equal 0. Okay, make the denominator equal to 0, and that's where the function is going to be undefined. Okay, so for this function, we're going to take the bottom, to take the denominator, and you set it equal to 0. So x cannot equal -2. Okay, that means if the bottom is equal to 0, the function's undefined. So x plus 2 can't equal 0, so x can't equal -2. Now, whether this is a vertical asymptote or a hole is going to depend on the rest of the function. It's either going to be a vertical asymptote or a hole in the function. Okay. Now, the only reason it wouldn't be a vertical asymptote is if you could reduce your function, if you could simplify your function and you had a factor on the numerator and the denominator that would cancel. If that happens for one of these x values, then it's a hole in the function. It's not an asymptote. Okay, so can I simplify the function that we have here? Can I factor anything and cancel? No. If I can't factor anything and cancel, then any 0 for the bottom, any number of x that you plug into the bottom and make it 0, is a vertical asymptote. So this one is going to be a vertical asymptote, not a hole. Okay, and we'll do one that's a hole later. All right, so step 1 is determine where the function's undefined, and then after you determine where it's undefined, you're going to simplify your fraction. You're going to simplify your rational expression by factoring and canceling. And once you do that, if the 0 doesn't cancel out, if in the simplifying you don't cancel that 0 out of the function, then it's a vertical asymptote. Okay, so we're going to simplify the expression and then decide, didn't want to do that, if the 0 is a hole or an asymptote. So in this case, it's a vertical asymptote. So right now, what do we know? We know that x equals -2 is a vertical asymptote. All right, so we have a vertical asymptote in at x equals -2. Now let's find the zeros. Let's find where does it cross the x-axis, where does it cross the y-axis. All right, so y-intercepts. How do you find where it crosses the y-axis? Okay, plug in x is equal to 0 into your original function. Now, if x equals 0 causes it to be undefined, then it doesn't cross, okay? Then it will never cross the x-axis. So when you plug x equals 0 in, if the function becomes undefined, then it doesn't exist. It means that that's an asymptote and you won't cross it. So plug x equal to 0 in, and what do we get? F of 0 is equal to 0 minus 1 over 0 plus 2 minus 1/2. So we know that this thing's going to cross the y-axis at minus 1/2. Okay, that's step 2. We're going to find the intercepts. Okay, what about the x-intercepts? How do I find those? Okay, x-intercepts. X-intercepts means when is the function 0? When is y equal to 0? That's the question. That's what we spend a lot of time doing in all of algebra, right? We say, all right, when is this function? To find the y-intercepts, we plug in x equals 0. To find the x-intercepts, we're trying to figure out when is the function 0, so we set the function equal to 0, and the way you figure it out is you set the top equal to 0. The bottom can never equal 0, so that's not going to be helpful. So if we say x minus 1 equals 0, x equals 1, that is the x-intercept. That's the 0 of the function. So when x equals 1, we cross the x-axis. Okay? So far we have 2 points and we have an asymptote. We still haven't built this thing. But let's take a look at it. If this is 1 point and this is 1 point, then you have a pretty good idea of which way this function is going to go here. This has to sort of do this. It looks like this function is going to approach that asymptote this way, right? It looks like that. So we should just confirm it before we decide. But if you have to go through those 2 points, the function probably has to do that. Okay, so far what we've done is we've got the vertical asymptote and we got the zeros, the x-intercepts and the y-intercepts. You get the y-intercept by plugging in x equals 0. You get the x-intercepts by setting the numerator of the fraction equal to 0. Okay, last thing we have to do is find the end behavior, and that's the horizontal asymptotes. Okay, now horizontal asymptotes mean when x is getting super large, positive or negative. What this means is when x is huge positive or when x is huge negative. What is y? What is y approaching? Okay, because a horizontal asymptote means you're never going to get there. So let's take a look at our function again. F of x is equal to x minus 1 over x plus 2. We've found the vertical asymptotes by setting the bottom equal to 0. We found the y-intercept by plugging x equals 0 in. We found the x-intercept by setting the numerator equal to 0. To find the end behavior, to find what happens to this function as the x's grow, positive and negative, there's a trick, but before I teach you the trick, I want you to try plugging in a huge number and see what you think is happening. So, huge number. Okay, so we're going to use 1,000 for a huge number and 10,000. X is growing. So what's the function? If x is 1,000, it's 1,000 minus 1 over 1,000 plus 2. This is end behavior. 1,000 minus 1 is 999. 1,000 plus 2 is 1,002. What is that close to? Okay, so this is approximately 1, but a little less. Let's put in a huger number. 10,000 minus 1 over 10,000 plus 2. Right? That's 9,999 over 10,002. What's that close to? 1. It's closer to 1. It's even closer to 1, but it's still on the small side. So you're coming at 1 from below. As x gets bigger and bigger, you're approaching 1 from below. Right? Now let's try it with some huge negative numbers. We're going to get x to be bigger and bigger, bigger negative, and let's plug in and just see what we get. So if x is equal to negative 1,000, when we plug in, we get negative 1,000 minus 1 over negative 1,000 plus 2. That's negative 1,001 over negative 998. What is that close to? 1. Bigger or less than 1? Bigger. This is bigger than 1. It's approaching 1 from above. It's a little bit bigger than 1. Right? And then if we plug in x is equal to negative 10,000, this is all end behavior is. End behavior, when you start specifying limits as x approaches infinity, it means as x gets bigger and bigger and bigger, what's happening to the function? So if we plug in negative 10,000, we have negative 10,000 minus 1 over negative 10,000 plus 2. So negative 9,999 over negative 10,002. Again, it's approaching 1 from above. That means that this 1, that's our horizontal asymptote. Now, I'm going to give you a trick on how to find that, but that's all the trick is going to do. It's going to assume that you've plugged in bigger and bigger and bigger values of x. Okay? Did my math wrong? I have a different negative 10,001. Let's erase that. See if I can do that. Sorry. Doing a different problem here. Negative 10,001 over negative 9,998, which is approximately 1, and it's from above. Okay, thank you, because you're slightly above 1. All right, so next thing. Okay, so I'm going to start off with our example. So we had x minus 1 over x plus 2, right? And what we just figured out is the limit as x approaches infinity of this function is equal to 1, and the limit as x approaches negative infinity of this function is also equal to 1. So that's what we just did with our calculations. But the rule is actually depends on the function itself. If we look at the function as a ratio of a of x over b of x, and we see these as a sub n x to the n plus ax plus a0, right? If we see these as polynomial functions, and b sub m over x to the m plus b sub 1x plus b sub 0. If we see it like that, the real question becomes, what is the relationship between n and m? That's how you're going to get n behavior fast. Okay, you're going to look at the highest exponent in the numerator, being n, and the highest exponent in the denominator, being m. So in our example, so here's our example, what's the exponent in the numerator? What's the exponent of x here, the biggest exponent? 1. What's the biggest exponent in the denominator? So they're equal. In our example, m is equal to n. That's what you're going to have to check on each one. You're going to have to check the relationship between those exponents. And based on what the relationship is between those exponents, you're going to be able to quickly get the n behavior. Okay, so if m equals n, so I just got to go back, then the horizontal asymptote is going to be a sub n over b sub m. So for, let's look at that again. Sorry, it's on the top was x minus 1 over x plus 2. All right, so in this case, if we emphasize this, our coefficients are 1, our exponents are 1. So this is n and this is m. Those are equal. And so the horizontal asymptote is going to be the fraction that you create by that ratio. So the asymptote for ours is going to be 1 over 1, and that's why we got a horizontal asymptote of y equals 1. Okay? Now, that's if m equals n. The other two cases are that m is greater than n. If m is greater than n, then the horizontal asymptote is going to be y equals 0, just like 1 over x, right? The power of x on the top would be 0. In this case, n would be 0 and m would be 1. M is bigger than n. That's the power, right? Because this is 1x to the 0 and this is x to the 1. Since the power on the bottom is bigger than the power on the top, you have a horizontal asymptote at y equals 0. Okay? And the last case, which is the hardest case, is if m is less than n, right? So for example, if we had x squared plus 3x plus 2 on the top, and on the bottom maybe we had x plus 1, right? I'll emphasize this. So what's m in this case? 1. What's n? 2. M is less than n. Okay. In this case, the n behavior will approach the quotient. So I would have to divide in x plus 1 into that. Okay, and the n behavior of this would be, the graph would approach the quotient of this. Now in this case, it actually would be the quotient because this is a factor. Okay, so let's do a full example all the way out. All right, so example, we're going to try to calculate the vertical asymptotes, the horizontal asymptotes, and all the zeros, and then get a reasonable graph. Okay, so f of x is equal to x minus 3 over x plus 2. Let's sketch a graph of that. Okay, so what we want to do is we want to get the vertical asymptote. We want to get the zeros. We want to get the y-intercept. And we want to get the horizontal asymptotes or the n behavior. And we're going to write it all out correctly and sketch it. All right, so vertical asymptote, how am I going to get that? Denominator equals 0. So where's my vertical asymptote? X equals negative 2. That's the vertical asymptote because x plus 2 cannot equal 0, so x cannot equal negative 2. All right, zeros. So these are the x-intercepts. Where am I? When is this function equal to 0? So we're going to say x minus 3 over x plus 2. We're going to set that equal to 0. When is y equal to 0? Yep. When x is 3, because we're going to take the top off and say, oh, this is going to be 0 when x is equal to 3. So we're going to start to sketch this out. We have a vertical asymptote at x equals negative 2. We cross the axis at x equals positive 3. All right, what about our y-intercept? How do I get the y-intercept? We plug in x equals to 0. All right, so if I plug in x equals 0, I get minus 3 over 2, which is minus 1.5. So that means that I'm going to cross the axis at minus 1.5. Okay, end behavior, horizontal asymptote. This is end behavior when we talk about horizontal asymptotes. What is the exponent on the top of the function? 1. The highest degree on the numerator is 1. What's the highest degree on the denominator? 1. Since these are equal, I'm going to divide the coefficients. My coefficients in front of the x in this case, it's a 1 over 1. So we're going to do 1 over 1. So the end behavior is going to be that we're going to approach the asymptote, the horizontal asymptote of y equals 1. Now, I didn't do a whole lot of work there, and I have a graph showing up. This graph is going to have to look like this. It has to go through these 2 points. Okay. Now, what about on the other side of that asymptote? Where am I? How do I figure out if my graph's up here or down here? So the way that you figure out what's going on one side of an asymptote, 2 things. So we need to figure out, are we above or below, right? So I'm going to show you a trick that's very useful, and you're going to use it this year and next year when you're talking about being near asymptotes. Since we can't cross the x-axis again, we know that it can't be there, so it has to be up here. Okay, so our graph actually definitely looks like this. All right, now another way to look at what's going on asymptotes, and this is going to be handy because sometimes you'll have several different zeros. Okay, so to visualize what's going on around an asymptote, you set up an XY table and set it up sideways. And this is actually a really useful thing to do, and you'll use this a lot when we do limits at the end of the year and when you go into calculus next year. So you put your undefined piece in the middle, and then you pick 2 points that are really close to that point. So really close to that point, I mean like off by 1/10 and off by 100th. So let's say that if we get less than 2, we'd be 2.01 and 2.1. Because the bottom was x plus 2, right? So the undefined piece is going in there. X can't equal negative 2, so we're going to put that in the middle of this table. And then we're going to go slightly to the left of that and slightly to the right of that. And when I mean slightly, I mean by like 100th and 1/10. Why does that keep doing that? Okay. Now, when I plug those numbers in, you're going to get a very quick picture of where this function is going as you get close to that asymptote. So we're going to take negative 2.1 and plug it in. Negative 2.1 minus 3 over minus 2.1 plus 2. That gives us on the top negative 5.1, and on the bottom negative 0.1. What does it mean to divide by 0.1? What's an easier way to divide by 0.1? So what this means is negative 5.1 times negative 10. That's the same thing. That comes out to be positive 51. That means you have to be above that horizontal asymptote. You're going up. Let's get the next one. So that was at 2.1. We're at 51. Okay, let's do negative 2.01. Negative 2.01 minus 3 over negative 2.01 plus 2. Negative 2.01 minus 3 is minus 5.01. Minus 2.01 plus 2 is minus 0.01. That's the same as negative 5.01 times what? Negative 100. So that becomes 501. And so as you get closer to the negative 2 line from the left, your graph is going up. It has to be going up. And you could do the same on the other side. And that's a really good tool to visualize what's going on near an asymptote if you don't have a graphing calculator in front of you. That's a very, very quick tool. And pick hundredths off. If you pick hundredths off, then you typically are multiplying by 10 or by 100. So pick powers of 10 off of that middle line. Okay, do you want me to do the other side, or you want to do another example? Other side? Okay, so let's take the negative 1.99 and let's plug that in. So I'll put that one up here. Negative 1.99 minus 3 over negative 1.99 plus 2. So this becomes negative 4.99 on the top, that's a minus, over 0.01. It's a positive on the bottom. Right? So negative 4.99 times 100 is negative 499. That means that if you are to the right of the negative 2 line, if you are on the right-hand side coming at that asymptote from the right, you are screaming down. You're getting bigger down. You're diving down to the negatives. So that's how you can see where these things are going without the graphing calculator in your hand. Okay, and if you did the next one, I think you'd get negative 49. It's going to get closer to that horizontal asymptote. Okay, let's do one more example. All right, go ahead and find the 4 things for that. Find the vertical asymptote, find the end behavior, the horizontal asymptote, find the y-intercept, and find the x-intercept. Let's do this one. So, vertical asymptote, x-intercepts, y-intercept, end behavior. Okay, vertical asymptote, what'd you get? Yep, Matt. 2, x equals 2. So we're going to put a line at x equals 2 because x can't equal 2. That's the vertical asymptote. Okay, the axis for it is x equals 2. The way that we got it is we said x minus 2 can't equal 0, right? So this is the asymptote equation, just to emphasize that difference there. Yep, x equals 2 is the asymptote. What about the x-intercept? Negative 3. It's going to intercept the x-axis. 2x plus 6 equals 0. So x is going to equal negative 3. So we have an asymptote at 2. Let's draw that in. We have an x-intercept at negative 3. Okay. Y-intercept. Negative 3. And we get that by plugging in x equals 0. So 0 plus 6 over 0 minus 2. We get negative 3. So y-intercept is also negative 3. All right, so you already see that these 2 points here, they have to connect. All right, but what about end behavior? What's the power of n? What's the n degree? 1, because this is a 1 up here, so that's 1. What's the m degree? 1, because that's a 1. So we're going to do the biggest coefficient, the biggest power coefficient divided by the biggest power coefficient. That's what we do. So what does this come out to be? 2. 2 over 1. We're taking this ratio, this 2 over 1, and that equals 2. So we're going to have a horizontal, our end behavior is going to approach this. So here's this side of the graph, right? And for the same reason that Sarah said on the other side is going to be up here, okay, because it can't cross the axis. Okay? All right, let's do one more that's slightly harder. Okay, so we're going to find this, but now on the bottom we have x squared, we have a quadratic on the bottom. Okay, so vertical asymptotes means the bottom has to be equal to 0. X squared minus x minus 6 equals 0. What is the easiest way to solve that? Without your calculator. Factor it. X what?
Minus 3 plus 2.
Minus 3, x plus 2. Those are the factors. So x equals 3 and x equals minus 2. These are the values that make the function undefined. That means that they're going to be asymptotes unless they cancel from the top. Do either of these two factors here, are either of those on the top? No, right? So this can be rewritten as x minus 1 over x minus 3 times x plus 2. Nothing cancels. So those are asymptotes, right? So if I look at this graph, it means I have an asymptote at 2, and I have an asymptote at, oh, did I do that backwards?
Yeah.
Sorry, I have an asymptote at negative 2, and I have an asymptote at 3. Okay. Okay, next, how are we going to get the zeros? Top has to be 0, right? X minus 1 is 0, so x equals 1. The only place that this graph can cross is right there. It will not cross that axis anywhere else. What about the y-intercepts, right? We're going to plug in x equals 0, plug that in, and we get 0 minus 1 over 0 squared minus 0 minus 6, positive 1/6. We're going to cross the axis here. We're going to cross that y-axis there. All right? N behavior. N is equal to what in this function? 1. And M is equal to? M is bigger than N, so the N behavior approaches. So the horizontal asymptote is 0. Okay? Now, how do you know which way you're coming at 0? You're going to have to test something on the outside. You're going to have to look at the outside. I don't know if I'm coming in this way or this way. I'm going to have to test a number out there. All you have to do is put one number in. Any number that is smaller than negative 2. So negative 3. If you put negative 3 into this, you get negative 3 minus 1 over negative 3 minus 3 times negative 3 plus 2. You don't even have to do this out. Watch. Top sign is what? What's the top? Negative 3 minus 1 is going to be positive or negative? Negative. The top of that's going to be negative. On the bottom, negative 3 minus 3 is what? Negative. Negative 3 plus 2? Negative. That means I have a negative divided by, what's a negative times a negative on the bottom? That means that it's negative. It has to be down in this area because it's a negative value. All right? Okay, so the homework for tonight.